Okay, so time to get started. Thanks y'all for coming. Glad to see y'all physically here. So new section to talk about. We're going to start with 7.2, surface integrals. A lot of this stuff is going to be kind of exactly what you would expect it to be. After all, we've already considered the idea of a domain that's kind of living in the wrong world, right? This is a surface here. This is intrinsically a two-dimensional thing, but it's living in a three-dimensional world, right? So it's dimensionally out of place. We've already talked about curves, which are one-dimensional things in let's say, a three-dimensional world. So again, dimensionally out of place. So how do we deal with this? Well, we make up a new appropriately tailored idea of a Riemann sum. This time, instead of chopping a curve up into little pieces that have little lengths, we're going to take this surface and chop it up into little pieces, each of which has little areas. And then on each one of those areas, we're going to talk about some sort of a density times that area, by which I mean quantity per unit area times area, right? And again, the goal is to get to turn a question about quantity, some accumulating quantity defined over your surface, to think of that as quantity per unit area times area, so that we end up with what looks like a Riemann sum. So no surprise as to how we're going to denote this. As usual, we denote that with that, loosely speaking, and we denote this with that, etc. So this is all, I think, pretty expected. We're going to call this a surface integral because the domain is a surface, and specifically we're going to call this a scalar surface integral because two things. First of all, the differential is a scalar quantity, and then also the integrand is a scalar quantity. So, you can flip back in the notes to where we first defined scalar line integrals, and I think you'll find it's very analogous. Okay, how to compute these things. Two ideas, again, that we're going to mostly steal from the past. We want to be able to change this domain into a different domain that we don't dislike, right? A less difficult to deal with domain. Again, we're going to do that by viewing it as an image, just like we did with change of variables. Just like we did with parameterizing curves, we can then pull back through that parameterization. In other words, rewrite everything in terms of our new parameter variables, S and T. Thus ending in a ds dt integral, as you can kind of look down to the bottom and see where this is going. Again, we're going to have to know some stuff about each little piece of area. And conveniently, again, we've already worked out a lot of that stuff. We did that last time, right? How big is a little piece of area that comes from a parameterization? Well, we found these little edge vectors and talked about the area of a parallelogram, et cetera, et cetera. And a bunch of details we already worked out. So it's kind of accidentally all over. We've already got everything that we needed to be able to do this pullback. So finally, here we go. Scalar surface integral. The ds that we have here, that little piece of area, we have this formula. Right? Whatever function it was that you were multiplying by area for whatever reason, maybe this is mass per unit area because in total you're computing area. Or maybe this is ants per unit area because you're computing total number of ants crawling around on your surface. Whatever. Right? That function just comes along for the ride. Of course, you're going to plug in for x, y, and z because you want to rewrite everything in terms of S and T. Okay. All right, and again, just as a last comment, we view this output area as being a multiple of this input area, ds dt, and therefore we can interpret this thing, the magnitude of capital N, as being our area stretching factor. which again, I think we all already sort of took that point of view last time. All right, let's get our hands dirty and do one. We're going to compute, among other things, the amount of mass that there is on the upper unit hemisphere over which mass is distributed according to that formula. All right, so now the very first thing we're going to do is recognize that this is going to be a scalar surface integral, right? So we are going to be looking at something kind of like this. And we know that in order to compute something like that, we need to have our stretching factor, which means we need our capital N, which comes from various partials of our parameterization. So step one's going to always be to parameterize. And so let's go ahead and do that first. Parameterizing our upper unit hemisphere. I'm going to use the spherical graph parameterization. We've used this parameterization a few times already. Might as well use it again. Yeah?
Is there like a specific reason that you picked this one?
But yeah, it's convenient. I mean, there are other alternatives, right? So I could, because it's the upper unit hemisphere and not the whole sphere, it is technically a rectangular graph. And so I could use the rectangular graph parameterization. Okay. If I did that, I'd have square roots in my equations. And so you have to choose between trig and square roots. And I have an example that's going to come up in a few days where I think I'm going to be able to persuade you that the trig is preferable. Yeah, right. Okay, so parameterization. And then, you got to take the appropriate partials and then take the appropriate cross product and then take the magnitude, right? And what you're going to find when you do all that stuff is sine phi. And again, I've waved my hands at that previously. With the follow-up suggestion that you fill in those blanks for yourselves. Again, I think that's a healthy exercise. I hope everybody will take a chance. Yeah.
Where did rho go?
Rho was 1. So because this is the upper unit hemisphere, right? And so that means rho equals 1. You might say that the rho is where I plugged in 1 to get this graph parameterization right here. Okay, well, it's all over but the plugging and chugging at this point. And so let's do that. Let's see here. Let's compute the mass. Now, I have a ritual that I like to do. I've mentioned this before, but I like to doff the cap to the fact that mass is an accumulating quantity. The whole is the sum of the parts, which, again, I think is a straight read right out of what I had written here. I just think that's a good, healthy starting point, easy to do. Now, of course, if the mass is distributed over area, then mass is density times area. From the previous page, we have that ds is stretching factor times whatever our parameters are, so d phi d theta in this case, right? Because those are our parameters. We were explicitly given in the statement of the question that density was Z. So mass per unit area is Z. We've already computed, conveniently, that our stretching factor is sine phi. It's just all plugging in. And of course, easy to lose track of things, but as you can see from our parameterization here, Z is literally just cosine phi. Right, so all I've done is plug in with our established formulas, and I have then turned our question into a double integral d phi d theta. This is all plug and chug, early chapter 5 computation problem at this point. Yeah.
Just to confirm, with phi and theta, it doesn't matter the order that you do.
Correct.
Okay.
Correct. That's right. Take your pick. In this case, anyway, because they both have constant mass. Effectively, we're over a rectangle. In some other circumstance where maybe phi might be a function of theta or something like that, then you might want to strategize. In this case, it doesn't matter. Yeah. All right. So now that was one computation. Notice this question actually said compute the mass, the center of mass, which is going to have 3 separate coordinates, and the moment of inertia around the z-axis. And I only did one of these 3 things. The big idea here is that the rest of these calculations are also integrals. They are integrals on the same surface, for which I'm going to use the same parameterization, and thus for which I get the same stretching factor, right? So a lot of the calculations going to be exactly the same, and you can see that sort of reproduction here, where if you look at all of this development of dm, right, all of that development of dm, you can see all of that in here. It's the exact same. And the only difference here, looking at the x-coordinate of the center of mass, is that inside of the integral there's an extra factor of x, which of course you can see from the parameterization is sine phi cosine theta. Everything else is the same. Everybody happy? All right. A couple more examples. If you want to take a look, feel free. And now on to one more example. And I want to remind y'all, when we were doing scalar line integrals, we saw several examples of how you can use scalar line integrals to compute various kinds of quantities, mass and the area of a fence and stuff like that. And then we looked at work. And stuff started being different. And we had to kind of recognize that what we were writing down was a qualitatively different thing. A lot of similarities, but significantly different. So that's where we're at now. We're going to try now another physical quantity. And it's going to turn out that this physical quantity, kind of like work, is going to just sort of change how this stuff is going to play out. So let's see how that works. We're going to be talking specifically about flux. Right, we talked about flux back in Chapter 3. We derived this formula. This formula, of course, does assume that we're talking about a flat surface with a constant vector field over that flat surface. Why were we interested in flux? Well, story, right? I mean, we're interested in flux because you can interpret it in these ways depending on what your assumptions are about what your vector field represents. Right? And so different metaphor, different interpretation of your vector field is going to give you a different interpretation of what flux represents. And reminder, that's all from Chapter 3. Okay. Right. So how do we deal if we have a non-flat surface? Right? Curved surface. Let's see. Let me change my colors. Curved surface, like so. Non-constant vector field, like so. Right? We can't just use the above formula. It doesn't even make any sense. So look, this being a calculus class, we pretty much always take things and chop them up into little pieces and then deal on the piece and then add them up, right? So on a teeny tiny little bitty piece of surface like this, it's approximately flat. Not exactly, but in the limit, close enough. And the vector field, now of course the vector field's not constant, but all the points in this little piece of surface are so close to each other, the vector field just doesn't have that much room, doesn't have that much time to be able to change that much. And so the vector field is approximately constant. Close enough in the limit. Cool. And so we chop it up, add it up, as usual. And here's where I have to pause before we get on to the details there. We have to recognize that there is something about flux that is fundamentally different from mass or population, and that is that the direction matters. Right? And so, again, flashbacks to earlier this chapter, I guess it was, but flashbacks to scalar line integrals, and then we developed this idea of vector line integrals. And one of the big first observations was that work depends on which direction you're going. Right? Mass doesn't. If you chop up a bent wire, the mass, I don't care which way you add them up. It's whatever. Who cares? right? Which way you paint the fence doesn't affect how much paint you use. But work, the direction really matters, right? So likewise with flux, if I say, here is my surface, and if I want to know the quantity per unit time of fluid moving through this surface, there's clearly something very different about the idea of fluid going upward through the surface versus fluid going downward through the surface. So there are two ways that I can compute what I would like to call flux that are clearly negatives of each other. So how do I distinguish the one from the other, and how do I decide which one of these is going to have to be called positive and one of them is going to have to be called negative, right? And so we have to decide first which direction are we going to call the positive direction through the surface. Again, not at all an issue for mass or center of mass or moment of inertia or anything like this. Direction doesn't matter at all. So the way we do it is with what we call an orientation. An orientation is just a collection of unit normal vectors that all have to have what I'm going to call a consistency about them. In other words, if I pick that normal vector here as drawn, then as I kind of slide over, there has to be a continuous clarity of which direction the normal vector points, and that kind of forces me to pick this vector here. Right? I can't just arbitrarily decide, I'm going to have this one be forward. Right? They all have to kind of fit together. So this is called an orientation. It's just, again, an arbitrary choice of which direction do we want to call the positive direction through the surface. Does not have to be upward. There's nothing magic about upward. How are we doing? Is everybody with me? Okay. So with all that, and then by the way, the vector itself we call the orientation unit normal, because that's what this unit normal vector does. It describes what our orientation is. Okay, that noted, here's how the calculation plays out. It's not that big a deal. Again, the whole is the sum of the parts. My little ritual, write that down first. On each little piece, if I want to know, how much flux is there through this piece of surface right here? Just this one little bitty piece of surface. Magnified for visual convenience, right? But this is an itty bitty teeny weeny little tiny little piece of surface. Well, again, it's approximately flat, and the vector field is approximately constant, so the flux is just the formula. Right? So d phi becomes that. And we find ourselves now with kind of an answer to our question. This is how you compute flux. This is our first formula, that is, for what you might call a vector surface integral. You'll see in a moment why we want to call it that. Sometimes, by the way, because of the close connection with flux, flux being the motivating example, sometimes we just call this a flux integral. It's a cool term. All right, now I want to again kind of remind y'all, I want to flash back to where we were talking about work. And let's see, let me write this out in blue. We wrote work was, of course, sum of a bunch of little pieces of work. And let's see here, it wasn't the first thing we wrote down, but an analogous thing that we wrote down was integral over a curve, f dot t ds. And this is one of our alternative versions of how to compute work. We actually came to that later. But anyway, perfectly acceptable way to write that. Now, let's think about our differential, what appears to be our differential here. And I claim that that's, not really, honestly, it's not really our differential. the differential, if you think about every other kind of integral we've ever done, the differential is the thing that carries all the information about our little piece of our domain. In single variable calculus, the differential is dx, because that's all you need to know about a little piece of the domain is how big is it, what's its length, right? Likewise for like dA and dV when we were doing double integrals, triple integrals. ds by itself does not tell us every single thing that we want to know about our little piece of curve, because our little curve has both a size and a direction that it points, right? So t indicates how that piece of curve is oriented. ds tells us how big it is. And between the two of them, that's what we need to know about our little piece of curve. So I like, and I think this is just makes loads of sense, to rewrite this. Whoops, sorry, back to blue here. This is a pretty common choice. To rewrite this as f dot dx, the idea being that the TDS, missed, sorry. The TDS is, this is telling us everything we need to know about our little piece of curve. The T tells us the orientation, ds tells us the size, and taken together, we call it the dx vector. And again, that is what I would call a true differential. This is telling us about our piece of curve. The vector field, what I would call the integrand, exists independently of our curve. Okay. Now, that's it. You're going to notice a pretty strong analogy here on a piece of surface. Looking at this form of our flux integral, what appears to be our differential, again, is only telling us size. ds scalar is only telling us how big the piece of surface is. It's the normal vector that tells us the orientation, right? And you need both of those. I need to know how big is it and how is it sitting in space, and how does so that I can understand how the vector field sort of cuts through it and stuff. So I need both of these in order to make sense out of my little piece of surface. And so in the same way that we have a convenient notation to represent dx, likewise, we have a convenient notation here to represent our little piece of surface, ds vector. Does that make sense to everybody? Everybody see the analogy of motivations there? Okay. So now I think you can see pretty directly how it is that this is what we would call a vector surface integral. Let me just clean up my mess here. Surface integral for obvious reasons. Right, our domain is a surface. And vector surface integral because our differential is a vector, and likewise our integrand, our actual honest-to-God integrand, also a vector. Everybody's happy. Okay. So how do we compute these things? Again, we already have all the machinery already set up inadvertently. Didn't even realize we were setting up what we would need for this flux integral construction. But here's everything we need. Apparently all I need to know is the ds scalar. Cool. Already have that. And combined with the normal vector, we can call that the ds vector. The parameterization, the idea of the pullback, all that stuff is all done. And here's the clever move with ds already established as this. I can now look at little n times the magnitude of capital N, and there's a real clever, convenient rewrite that I can do on that. Now, as I rewrite this, I'm going to commit a little math crime. I'm doing it on purpose. I'm doing it for a combination of dramatic purposes and to prevent a distraction by there's a whole long conversation we're going to have about what I'm currently hoping to just gloss over, right? So that we can kind of let's get one in the win column. Let's get some experience under our belt first. So I'm going to argue inappropriately as follows. This product here, well, I know it's pointing in the direction perpendicular to the surface. Well, so does capital N. This product has magnitude, which is the magnitude of capital N, just like capital N. This product here, little n times the magnitude of capital N, seems to be pointing in the same direction and having the same magnitude as capital N. And so I invoke the looks like a duck, quacks like a duck argument. And feels like this ought to be capital N, shouldn't it? Hard to argue with? If you think you have a theory as to why this is wrong, good. Sit on it. I'll fully confess my crime momentarily. So for the moment, I'm just going to say asterisk. Again, this is a little bit wrong, and I'll fix it later when I think it's a more appropriate time. Okay, so anyway, look at our convenient little result here. Everything here is all fully pulled back computation of flux. Everything in the big dark blue circle here is in terms of S&T. And so easy computation. Example. Let's see here. So computing a flux. Oh, actually, let me do it like this. Computing a flux, and so we're going to use the formula we just established. For which purpose I am going to have a parameterization. All right, so we're going to have to take our surface, graph parameterization, take the partials, take the cross product to get our capital N. Right now, if this were a scalar surface integral, we would have to compute the magnitude. But notice, very conveniently here, nowhere in this formula that we're about to plug into does it explicitly require having the magnitude of capital N. It's not there. I mean, it's hidden inside of our actual capital N vector, but I don't need to know that magnitude explicitly, so I don't need to compute the magnitude. It's just kind of already in there. That's very convenient. And with that all done, then our color mistake. Our capital N vector is that. Let's see, our F vector. Now, of course, we're given the F vector. It's that, which I claim is going to simplify to that. So what happened there? It is easy to get this wrong. It's easy to kind of get confused as to what happened to the x, y, and the z, and how did I get rid of the x, y, and z. And don't forget, when you are parameterizing, when you are pulling back through a parameterization, the parameterization itself tells you your x, your y, and your z. So, for example, this z right here. Now, there it is. It is explicitly part of what the parameterization is. Likewise, this x, what's the deal with that x? Where am I going to find x? There it is. Whoops. It's S. And likewise for y. Is everybody good? Okay, and let's see here. We were looking for the portion sitting over the unit square. Now, there's a little subtlety here, I suppose. Above the unit square, what this means is I'm looking for the part of this paraboloid where x and y range over the unit square. How am I going to make x and y range over the unit square? Seems like a hard one, but keep in mind, x and y are S and T. So I want S and T to range over the unit square, and thus these bounds. Everybody okay with that? Okay, and then plug and chug, right? And it's just iterated integral, dot product and an iterated integral from there. It's all polynomials. This is an easy one. Okay. All right. So what was my crime? What did I do wrong? It has to do with this natural question of, does the parameterization matter? And let me just remind you, when we've previously seen formulas like this one, where something that is intrinsic to the surface and vector field is computed with a formula that seems to depend on what your parameterization is, because this is chock full of parameterization. Do I get to pick any parameterization I want? It seems like that would give me different answers. Surely there's a right parameterization. Mostly, doesn't matter. There's asterisk, right? But mostly, the parameterization is irrelevant. But it does matter a little bit, and this is, again, pretty analogous to what we saw with vector line integrals. You have to parameterize in the correct direction. And very counterintuitive, because when we parameterize a surface, we don't tend to think of the parameterization as having a direction. Now, just for contrast purposes, let me draw a quick picture here in the corner. And here is a curve, 2 endpoints. And the curve, if I were to parameterize it, of course, that parameterization would have a direction. Because, after all, a parameterization we think of as position as a function of time. That suggests movement. That suggests which way we're going. I mean, it's right there in what a parameterization is. Right? And so, whether you think of just how this curve gets traced out, or whether you compute the velocity and see which direction the velocity vector points, or whether you just think, all right, where am I at t equals 0, and where am I at t equals 1, right? Or whatever your bounds are. One way or the other, it's usually pretty clear which direction you've parameterized a curve. We just don't see that when we parameterize surfaces, because we don't have that time metaphor, right, to kind of be able to develop that intuition. But it remains that when you parameterize a surface, you are parameterizing in a direction. As follows. Suppose you have a surface. Oh, again with the highlighter. Let's see here. So surface. If you're going to talk about flux through a surface, well, again, you have to be clear which way is the positive direction through the surface. And there's 2 possibilities, right? Whoever is asking the question needs to be clear in their mind, which direction is the positive direction for flux? And we do so with as previously discussed, the orientation unit normal. Fine, and then we parameterize. The parameterization determines those partials, which therefore determines this capital N vector, which therefore determines a normal, right? A unit normal telling you which way you're parameterizing. And this unit normal directly follows from how you chose to parameterize your surface. So, depending on what normal vector you were supposed to do, right? Let's see here. Let me just erase these. If you were supposed to parameterize the surface this way, cool, you got it right. Right? 50-50, coin flip, you happen to get lucky. But what if you were supposed to parameterize it that way? I mean, when we write down a parameterization, we're not really usually thinking about which way we're supposed to be parameterizing. It's just not on our minds. When I parameterize, I'm thinking graph parameterization or create your favorite coordinate system or tweak an existing parameters. I'm just not thinking about directions. Right? So if this kind of thing happens, then you were supposed to parameterize it that way, but apparently you accidentally parameterized it that way. And you parameterized it backwards or upside down or however you want to say it. Does that make sense to everybody? And going back to the analogy, thinking about this scenario, if I can get this thing, there we go. Well, kind of, here we go. Okay. If you were supposed to parameterize the curve as indicated, and the question had been to, let's compute the amount of work that it takes to go in this direction along that curve. If you parameterize like that, you parameterized it wrong. Right? You're going to get the wrong answer. Now, conveniently, you will get the wrong answer by exactly a factor of -1. And that exact factor of -1 is easy to just kind of throw in at the end. And we did an example like that some time ago. And that is handy, and I'm all for it. So, in fact, that's what we're going to do in this scenario. I am not suggesting by what I've drawn here that you should be thinking about which direction you're parameterizing things as you're parameterizing things. It's too much trouble. It's hard to see it coming. It's not that it can't be done, but I don't think it's worth the trouble. My advice is parameterize it however you want. Whatever's most convenient. And then just at the appropriate time in the calculation, which I'll show you in a second, just make sure to look and see, wait a minute, which way did I parameterize it? And then look at the statement of the question, in which direction was I supposed to parameterize it? And ask yourself if you did it right or if you did it wrong. And if you did it wrong, no big deal. You're just off by a -1. Just throw in an extra factor of -1. Nothing to it. To fill in from the previous page, here is the just kind of a repetition of my math crime, right? So this is what we were looking at, where I argued that this looked like a duck and quacked like a duck, and therefore it must be a duck, right? Well, the thing is, I conflated two different things, keeping in mind, when you're asked to compute flux in a given direction, the orientation unit normal defines which direction you're supposed to parameterize things. When you actually parameterize and come up with your capital N vector, there is, on the other hand, the parameterized unit normal that's implicit in how that capital N vector works out. And I just declared those to be the same, which was baseless. All right? This is a coin flip. It's 50-50 as to whether those are going to be the same. I can't just assert that they're going to be the same. So that was my crime. Is everybody comfortable with that? Everybody see what's wrong? Yeah.
Wait, sorry.
Mm-hmm.
I just have a question about the diagram.
Yep.
So does n equal to n times the length of n?
So the claim that I had made was that capital N was equal to little n times the magnitude of capital N.
Oh, okay, yes.
That had.
Looking at the lecture notes, it kind of looks like the integral is equal to that. So yeah.
Oh yeah, no, I'm just focusing on just the assertion that this should equal to this, aka should equal to this, and I'm claiming that they're not. This is, maybe they are, maybe they aren't, but as a broad statement, they are not the same. Yeah. Right. Okay. All right, so mea culpa. Let's see here then. Let's do one. Oh, sorry, real quick. I want to do one last thing up here where we had developed this formula for how to work out a flux, right? When it's very convenient. And this is, again, not really quite right. Loosely speaking, what I've kind of done here is rewritten the ds vector as capital N ds dt. And again, that contains the mistake. That contains the whoopsie here where there's a plus or a minus and I don't know which one it is inside of what I have circled in blue here. So the correction then is to, let's just recognize that, there is a possibility that I might have parameterized upside down, and so, heads up and do be careful. Make sure that you parameterize the correct way. Okay, and then real quick before we go into the details, other than the orientation nonsense, you don't have to worry about anything else concerning parameterizations. Other than orientation, parameterizations don't matter. Okay, so let's revisit the last example, this time a little different, this time designed for us to accidentally parameterize it the wrong way. How would you tell, and how do you fix it? So here we go. Same example before. Computing flux, same vector field, same portion of the same surface. The only difference being that now it's oriented downward. Reasonable question. How do we deal with this? Well, surface, we parameterize. We take the appropriate partials. We take the appropriate cross product. All of that's very mechanical. That's just, it is what it is, right? And before we finish this calculation, we don't really have what we need to decide if we parameterize right side up or not. Looking at this formula right here, for example, very hard to see whether this is right side up or upside down. You just can't see it really quite, right? But from here, you can totally see. After all, my normal vector is clearly pointing at least somewhat up-ish. I was supposed to parameterize it in the downward direction through the surface, not in the upward direction through the surface. So what I have in the comparison between what I was supposed to do and what I actually did, I got it wrong. It's pointing the wrong way. Okay, so how do we fix it? Nothing to it. Easy to fix. I just recognize that I got it wrong, and so I account for this by a minus sign. And now we're fixed. That's all good, and we can just plug and check. Yes?
It's not really intuitive to me why you decided that this is facing the wrong direction.
Right. Okay, so let's draw a picture of our surface here. Our surface. You know what? I actually already have kind of a decent picture. Now, keep in mind this is a paraboloid, right? So let me just scroll to where I have a convenient picture of a paraboloid, right? Here is our let me do it like this. Here's our paraboloid. And the two possible orientations are this one. This is what I'm calling upward, right? And this one, this is what I'm going to call the downward orientation. Right? Now keep in mind, an orientation is just an indication by way of normal vectors of which way is considered the positive direction. Well, we were supposed to parameterize downward. That's the positive direction through the surface, right? When we wrote down our normal vector up here, you can see right here our normal vector. If you look at that third coordinate's positive. That means that this normal vector is it's not this, right? It's not down. It's above the horizontal, right? And being above the horizontal, it's going to have to be one of these upward-ish things, not downward-ish. So I was supposed to parameterize to give me the light blue normal vectors, and based on the capital N vector that I see, I did it the wrong way. Is that satisfying?
Yeah.
Everybody else? Is that cool? Yeah.
Is there ever a case that that z portion of the normal vector would be 0?
Oh, sure, yeah. No, there's a variety of different cases, and the geometry of every example is always going to be a little bit different. And so, the z coordinate alone is not always the best tip-off. And I'm going to come in a moment to talk about different versions of this. Yeah, absolutely. So what we've done here really only applies in this case.
Okay.
Yeah. All right, so we're basically done with this example. There's just a couple more little details I want to point out. First, we have seen here how to identify that, we screwed up, right? We parameterized the wrong way because, again, with the upward and the downward, that's a mismatch. So we got it wrong. Now, how do you fix it? Aside from we know there needs to be a minus sign in there. What you can't do, and now this is, I guess you might say, more of a matter of course policy at this point, please don't just literally just have a minus sign that appears out of nowhere, right? Because I don't know where that came from, right? So that's not sufficient. Do keep in mind, I know you've heard me say this a million times. I say it over and over because it's that important. This is a class about reasoning, not answers, right? So the explanation you provide for where that minus sign came from won't affect how the answer turns out. So what? That's not what we're interested in. I'm interested in the reasoning. So you have to give me some documentation, however little, as long as it's clear that you are making a clear connection between how you were supposed to orient it and how you inadvertently, accidentally oriented it. That's all I need. So in this case, given what I have written down, I think a pretty reasonable solution would just be that right there. Notice I didn't even have to write anything, right? I drew a connection between what I was supposed to do and how I see what I inadvertently actually did. And drawing the line to the minus sign is a pretty clear indication that I'm recognizing that these are incompatible. And furthermore, is the clear explanation for why I put that minus sign in there. So again, you don't have to write a book, right, for every little thing. But this is where that minus sign orientation negative comes from is a significant idea, right? That's important part of the class. So you got to give me something, but this, what I've done in green here, I think is plenty good enough. Does that make sense to everybody? Okay, one last thing I want to point out. It is actually important where you put the minus sign. Some students will do the following, and this is just wrong. Some students will say, hey, I was supposed to do it downward. This is upward, and I'm going to fix that. And then they put the minus sign here on their formula for in. Or maybe down in the equation, inside of the in vector. And that's not right. The formula for capital N is not changed. Capital N is something that is intrinsic to the parameterization. Capital N is this cross product that comes from the parameterization. Whether it was what it was supposed to be or not does not affect the fact that this is what N is. So putting the minus sign there is a mistake. Now again, that won't affect your answer. I refer you to my earlier comments. Don't care about the answer, right? If you put the minus sign in the wrong place, then your formula for capital N is wrong, and then furthermore, since there wouldn't be a minus sign here, your formula relating ds to capital N ds dt would also be wrong. That'd be two sign errors, not zero sign errors. It's zero sign errors in the answer that we don't care about. It's two sign errors in the reasoning that we do care about. Yeah.
So we should just put a minus sign in front.
Yeah. That's right. When you make the transition from, keep in mind, ds comes from the given orientation of the surface, right? So that's a surface thing. In is a parameterization thing, and the minus sign goes in recognition of the fact that these are opposites. Yeah, totally. Is that cool? Is everybody happy with that? Okay. All right. Oh, and I while we're here, just for fun, let me point out another thing that you can never do, and I do see this sometimes, where students will take will take a this calculation, and then they'll come up with an answer of 6, and then in their minds they'll realize, whoops, I parameterized this upside down, and then they will say equals -6. Now again, if the goal is only and strictly only the answer at the end, okay, I guess that does get the correct final value. But notice the presence on the page of the equation 6 equals -6. You should never, ever, ever have that on your page under any circumstances. So I hope that makes sense. Again, you can't just throw stuff in willy-nilly. It matters where it goes. Okay. All righty. Let's see. How are we doing on... Oh, we're out of time. Sorry. So we're ending right there. See y'all later. Have a good Thanksgiving break. And we'll pick up here on Monday. So yeah, see you in a week.